some more review, but we'll kind of let these topics settle in twice to get that done. So, you don't need your calculators. Just I'll do this for you. But when we're exploring what we call limits, we're going to look for, and the notation here says, find the limit as x approaches 0 for this function. Okay? So, first of all, being able to read it properly and understand the notation. This again is find the limit as x approaches 0. That's a little arrow for this function. So as our x coordinates get closer to 0, now 0 would be right in here. Agreed? Okay, so if I were to plug in 0 on a table of values, I would get the sine of 0 over 0. And what is the sine of 0? 0. And 0 over 0 is undefined. So the function itself doesn't have a value at 0. But we're going to look at what happens if our numbers get closer to 0 coming from the negative side. Can we see how negative 1/10 and then negative 1/100th and then negative 1/1000th, that's getting closer and closer and closer to 0 coming from the negatives. And then we're going to get closer and closer and closer to 0 coming from positives. Because the limit does not necessarily mean what is the function value there. Because the function value is clearly undefined. That doesn't mean that it doesn't have a limit. And a synonym for the word limit is like the intention of the graph. So even though it's undefined there, the graph still might be intending to approach a certain number. So when you think of limit, what is the graph's intention as it approaches, in this case, as your x-coordinate approaches 0? So I'm just going to type in, and my calculator should be in radians, mode radians, okay? So I'm going to do the sine of negative 0.1 over negative 0.1. And I'm just going to copy that down, 0.998. And then I'm going to do the sine of negative 0.01 divided by negative 0.01. And I get 0.99998. And then one last time coming from the negative side, the sine of negative 0.001 divided by negative 0.001. And I get, oh boy, thank you, 1, 2, 3, 4, 5, 6 nines in a row followed by an 8. So 0.9999998. So as my x-coordinate is getting closer and closer to 0, coming from the left, or coming from the negative side, what are these numbers getting closer and closer to? 1. Okay? So this notation down here, you're going to have a superscript on your 0 a lot of the time. That does not mean the limit as x approaches negative 0. We're still looking for the limit and the intention of the graph as it approaches 0, but coming from the left side. And that's what we just looked at here. Coming from the left side, the value of the function is getting closer and closer to 1. And then we're going to do a similar thing coming from the right side. So I'm going to start at positive 0.1. So the sine of 0.1 divided by 0.1 is 0.998. And then I'm going to do 0.01. Sine of 0.01 divided by 0.01. 0.99998. 4 nines and then an 8. And you can see it's kind of symmetrical on either side. Every function's not like this. This one just happens to be. The sine of 0.001 divided by 0.001. And then there's your 6 nines again followed by the 8. So as we're getting closer and closer and approaching an x value of 0 coming from the positive side of things, this is also increasing towards 1. And so down below, your superscript of x is approaching 0 from the right is 1. Now I will show you a graph of this function, the sine of x over x, just to make sense of it all. I'll do my window from negative 2 pi to 2 pi and a y value of, I think just because I know what it's going to look like, 0 to 3 will be plenty. Oh, that's not what I wanted. 0 to 3. So this is what that graph looks like. Now, you guys can't tell because your graph doesn't do a very great job of showing holes, but there's a hole right there at 1. If I did second trace value and I looked for the value of this graph at an x-coordinate of 0, and I already showed you via plugins, you're going to get nothing because it's undefined there. But as we approach 0 coming from the left, the intention, anyway, of the graph is to reach 1, even though it never does. And as you approach 0 coming from the right-hand positive side, the intention is to hit 1, even though it doesn't. So visually, it makes sense that we're getting closer and closer to 1, but there's a hole there, so we never reach it coming from both sides. Okay? And as long as they match on both sides, then the overall limit, and by the way, if they don't match, then the limit won't exist. But it's very clear that no matter what side you come from, the intention of this graph is to hit 1, and therefore this limit, as you approach 0, because it's the same on both sides, is 1. So this graph, if I wanted to sketch it down below, if this is 1, there's a hole there. It's an open circle, and then it kind of does that on both sides. And it will, I believe, go above and below. Like if I do, let me just do like my, I'm going to do my y window from negative 1.1 to positive 1.1. And this from like negative 2 pi to 2 pi. Yeah, it does go above and below. And it actually, I only went from negative 2 pi to positive 2 pi. If I went negative 4 pi to positive 4 pi, you'll see even more so what it does. It actually oscillates surrounding the x-axis, but with less and less of an amplitude as it goes out. Okay, so if you want to be a little bit more exact than that, it goes down, then it comes up, and it kind of goes down by a lot at first, but then by less and less. Okie doke? All right, so here's the important takeaway. In the function, f of 0 is undefined. We showed that above, because when you plug in 0, you have a 0 in your denominator, and it's undefined. But the limit as you approach 0, the limit of this same function as you approach 0, meaning the intention of the graph is to hit 1. And so the function value does not have to equal the limit of the function value. Sometimes it will. A lot of times it will, but it doesn't have to. And a lot of times, the more interesting examples that we will look at will be cases when they don't match. Okie doke? All right. So, we'll take this function, for example, and we'll look for the limit of this as x approaches 4. So we're going to, 4 is right here. We're going to come at 4 from the lesser numbers, and we're going to come at 4 from the greater numbers. So this side will be giving us the limit as x approaches 4 from the left, from the lesser numbers. And it's always the limit of your function, and our function here is 3x squared. Whereas the right-hand side will be the limit as we are approaching 4, an x value of 4, coming from the right-hand side, so the limit of the function 3x squared. So we'll essentially figure out what that equals coming from the left, what that equals coming from the right. So, just really quickly, 3 times 3.9 squared, 45.63. 3 times 3.99 squared, 47.76. And then 3 times 3.999 squared, 47.976. So what number does this appear to be getting closer to? 48 maybe? And if you didn't know, and even though the chart doesn't call for it, you could type in 3.99999999999. Isn't that getting infinitely close to 4 coming from the lesser side squared? And eventually your calculator gets sick of rounding, and you can kind of see that it even though it doesn't actually equal 48, it probably equals 47.99999999999, and so on. The calculator just cuts that off and rounds it accordingly. So that is getting closer and closer to 48. And then if I plug in, starting with 4.1 and working my way closer to 4 from the right, 3 times 4.1 squared is 50.43. 3 times 4.01 squared, 48.243. And then 3 times 4.001 squared, 48.024. So you can probably see that it's also approaching 48 coming from the right, but if you weren't 100% convinced, 3 times 4. Just do a ridiculous number of zeros followed by the 1, 0.0, all those zeros, 1, squared, and again, your calculator will just give it to you. Okie doke? All right, so these are both 48, and so your overall limit as you approach 4, since coming from the left and coming from the right match, your limit of the function 3x squared is 48. Now, this problem doesn't ask us to do it, but what is f of 4? Never mind the limit as we approach 4. What is f of 4 if f of x is the function 3x squared? 48. So this is a case where the function value and the limit value do match. They didn't on the last one because we actually got an undefined on the last function value, but they do here. Okay, and if I were to quickly just sketch this graph, I'll do it. We all know what it looks like, right? It's an exponential parent graph tripled. So it's super tall and skinny. And so your point, 448, let's just pretend is right there. I think we can all agree that as we approach that point from the left, our y value is getting closer to 48. If we approach that value coming from the right, our y value is shrinking also towards 48. And it makes complete sense because that is the function value. Okie doke. So I guess we just did the next section without me realizing it. Use the graph of f of x to find the limit. So I'm using this graph and saying, okay, as my x-coordinate is getting closer to 4 coming from the left, my y-coordinate is getting closer to 48. As my x-coordinate is getting closer to 4 coming from the right-hand side, my y values are shrinking towards 48. You can see them growing towards 48. You can see them shrinking towards 48. So that was 48, and we already did f of 4 was 48 and talked about that. Okie doke? Okay. So cases where, just like the types of things we'll be looking at, which kind of shake things up a little bit, like piecewise functions are tricky Because, just a couple examples, in a piecewise function, you could be approaching something from the left and approaching something from the right, and they're different numbers, right? So you'd have a limit coming from the left, that would be the graph's intention coming from the left. You'd have a limit coming from the right, that would be the graph's intention coming from the right, but they don't match. So the overall limit doesn't exist. But the function value does, it's where the solid circle is. So there's there's a lot of different scenarios. Maybe they both exist and they're the same, like in this one. The limit from the left, the limit from the right, and the function value, they all exist and they're all the same. In this case, the limit from the left and the limit from the right and the function value all exist, but two of them are down here and the third one's up there. You could have a limit from the left, a limit from the right. So there's an intention coming from the right, there's an intention coming from the left, and they're different, and the function value could be totally different in a piecewise function. So all three of them could be different. You could have the two limits coming from the left, coming from the right, have the same intention, but the actual function value is different. So lots of different scenarios. So this next one asks us to graph the function. And just a reminder as to how to graph piecewise functions. There's the first piece wants the line 2x minus 4 all the time except for when x equals 3. So we want to defer to the line 2x minus 4, which is a y-intercept of negative 4, and a slope of rise 2, run 1, rise 2, run 1, rise 2, run 1. So there's my line 2x minus 4, and it wants that line everywhere except for where x equals 3. So at x equals 3, 1, 2, 3, on the line, which just puts me right there, I don't want that to be an open circle because my line only exists everywhere else. So my line does not exist there. And then the second piece says, well, here's what I do want. When the x-coordinate is 3, I want a y-coordinate of negative 5. 1, 2, 3, 1, 2, 3, 4, 5, which would put a solid dot right down there. So I'm going to do that. So in order to find the limit as x approaches 3, before I do that, I have to look at the limit as we approach 3 from both sides. So if I'm looking at this function and I'm approaching 3 from the left, that's over here, and I'm getting closer and closer to an x value of 3, my y-coordinate is getting closer and closer to what? Two. Which you just kind of figured out because you were thinking up 2 over 1 probably. But you could, because that's just a whole, you could go ahead and just plug 3 in and say, okay, well 6 minus 4 is 2. So that's where the whole is. That's where the graph's intention was. So as I approach it from the left, it's approaching 2. And as I approach 3, coming from the right-hand side, I'm also approaching a y-coordinate of 2. So do those match? Yes. And because they match, then the overall limit exists as well and is 2. Versus, what is f of 3? Negative 5. Now, I'd say without getting too far ahead of ourselves, but this is down the road. When the limit exists and the function value exists and they're not the same, this is what you would call a discontinuous graph. And discontinuous means exactly what you would think it does. It's not a continuation. You have to, like, if you were drawing and tracing along it, you'd have to pick your pencil up off the paper, hit this other point, and then pick your pencil back up and restart. Versus when they all match, the limit from the left and from the right makes the overall limit exist, and the limit value matches the function value, it sort of plugs up what might otherwise be a hole, and it connects it, and you just can smoothly draw that entire graph without picking your pencil up off the paper. Does that make sense? So would this one be continuous? No. This would be considered discontinuous. Visually, because I have to pick my paper or my pencil up off the paper because I have a hole that I have to jump over. Algebraically, it's because the function value and the limit value aren't the same. If they're the same, then there's no need to pick your pencil up off the paper when you look at the visual. Okie doke. So the continuous stuff is me getting way ahead of myself. We'll have a whole day on like what that definition is and evaluating that for different cases. But your homework for tonight is 1 through 25 is odd, except for I decided that between 5 and 17 you only have to do 5s and 7s. Okay?